Good morning, chemistry students. I'm going to introduce the next chapter that we're going to be going through. We're going to kind of combine chapters 4 and 5 because they both really talk about development of modern atomic theory and some of the people that played an important part in that atomic theory development. So in this first section of chapter 4, we're going to talk about Democritus' very early theory and John Dalton, who came up with, although it was a long time ago, a much more modern atomic theory that we have built on since that time. And we're going to identify some of the instruments used to observe individual atoms. We'll talk about that a little bit and some of those processes just briefly. So we define atoms are the smallest unit of an individual element that can be seen. If you have, for example, a sample of anything like gold or any pure element, you can continue to cut your sample in half and have smaller and smaller and smaller units. But there comes a point in time where you have reduced your sample down to, by cutting it in half, down to one individual atom. And you cannot cut it any smaller than that, because if I take an atom of gold and cut it in half, it's actually not gold anymore. So at some point we reach the very, smallest unit that you can have and have it still be gold would be one atom. Atoms can be seen, some of the larger atoms can be seen with scanning electron microscopes. So we might be able to see the individual atoms, but we really can't see those subatomic particles, those protons, neutrons, and electrons. Those actually can't be seen. So what we know about them are really based on inferences that we have made based on what we actually have seen occur with lots and lots of experiments that have been done. So where did the theory of atoms begin? It actually began with someone in ancient Greece named Democritus. So Democritus actually came up with the idea that, hey, I think everything that we know of is made of these tiny little particles called atoms. And he said, I think atoms are both indivisible, so cannot be divided, and they are also indestructible. His theory, although pretty awesome, was not very scientific because he really didn't have any proof. He actually had a name for these individual atoms, or the different types of atoms that he believed existed. So his theory was that there are 4 of these types of atoms, if you will, that make up, in different combinations, make up all the known things in the universe. So he thought that, so humans were made of different combinations of earth, air, fire, and water than, say, a rock. But again, he didn't have a lot of proof, so this was him just sort of thinking outside the box, if you will, for his time in our world. But it's actually pretty awesome that he came up with the idea that there were atoms. He's not quite right about the numbers of different types of atoms, and certainly, Earth itself is not one particular atom. So, but still, forethinking for his time. It wasn't until the early 1800s that someone by the name of John Dalton developed a theory that was a little closer, or a lot closer, to what we believe in modern times. So John Dalton developed the following theory based on the results of chemical reactions. So he looked at all the chemical reactions that had been done and the results that they produced, and he said, hey, I think that all elements are composed of tiny indivisible particles, and we're going to call them atoms. So these tiny indivisible particles called atoms. And so that was his first postulate. The second postulate, atoms of the same element are identical. Okay? So if I have 2 atoms of gold, they are exactly identical in structure, in mass, in numbers of subatomic particles. They're identical in every way. They react the same way and so forth. The atoms of any one element are different from those of any other element. So if I have an atom of gold and an atom of oxygen, we would expect that they would be structured differently. That's true. We know that to be true still today. His third postulate of his theory, atoms of different elements can physically mix together or can chemically combine in simple whole number ratios. So that's important, that they always stay in whole number ratios. So that means if they physically mix together, it just means I can take some atoms of gold, I can take some atoms of silver, and they mix together. They don't really combine chemically, but they're going to stay in that same. They are going to stay whole, and they're going to retain their properties if it's a physical mixture. But they also can combine chemically in whole number ratios to form compounds. And so we would say something like, if I have 2 hydrogen atoms and an oxygen atom, right? So hydrogen and oxygen combine in whole number ratios to produce water. It doesn't take 1 hydrogen and then half of an oxygen. There's no such thing as half of an oxygen. They have to combine in those whole number ratios because, remember, we said they're composed of indivisible particles, so we can't cut them in half. So again, this is true of all compounds, carbon dioxide, even compounds like, sugar and things like that. Chemical reactions occur when atoms are separated from each other, joined, or rearranged in a different combination. So so chemical reaction, if I combine something like, if I combine hydrogen gas and oxygen gas, they combine to produce water. So that's a new compound. Okay, so they're joined together, rearranged in a different combination. Something has happened where a chemical bond has either been formed or a chemical bond has been broken. We do, it's a little bit smaller, we do have to, so these were, remember that this was written in the 1800s, so things have changed a little. We actually would say atoms of one element, however, are never changed into atoms of another element as a result of a chemical reaction. So is this true? Well, for everything that we do in this classroom, it's absolutely true. However, there are cases in which atoms of one element actually are changed into other elements. This happens naturally on stars. Oh, this is so. So stars like our sun, that actually happens. Also in things like nuclear reactors, or anything that we classify as a nuclear reaction. Those are all things that actually change. They split an atom, or they fuse 2 other atoms together, fuse particles together to make a new element. That's actually how the man-made elements are made. And remember, there's lots of them. now. So we know that although John Dalton was kind of right in his time based on what they knew at the time, but we know that this actually has changed and is not really true anymore. So now we say of this, we say that this is true in ordinary chemical reactions. So in an ordinary chemical reaction, that is still true. We just, it's an ordinary chemical reaction. We're not in here in this class. You will not be splitting atoms. You will not be combining atoms or creating new elements. There's no way that we have the very, very expensive lab equipment required to do that. So we do say in ordinary chemical reactions. All right, I'm going to breeze right into section 4.2. Not the whole thing, we're just going to talk about the first part. So identifying the three types of subatomic particles. I'm sure you're very aware of what these are already, but we're going to share probably a little more information than you may have from previous courses. And then we're going to talk about all the different scientists that helped develop that modern atomic theory and those particles and behavior particles and so on. So I'm sure you are well aware, unless you've grown up under a rock somewhere, that or never taken a science class, but I'm sure you've heard of protons, neutrons, and electrons before. This isn't new information for you, certainly at this point. However, protons are the positively charged particles that we find in the nucleus of an atom, so that's where they're found. Neutrons are also found in the nucleus of an atom. Both of these, protons and neutrons, are responsible for atomic mass. Electrons are so tiny, we really don't even consider the mass when we're looking at the numbers of electrons. But protons and neutrons give an atom its mass, and that's an important property. Protons specifically give an atom its identity. So, for example, if I look at the periodic table, I see element number 6 is carbon. Any atom in the universe that has 6 protons, because the element number is the number of protons, any element with 6 protons is carbon, regardless of any of the numbers of other particles or any of the other properties. If it has 6 protons, it is carbon. If it has 7 protons, it is nitrogen. If it has 8 protons, it's oxygen every single time, because that number of protons is what gives an atom its identity. That's how we determine what element it actually is. Neutrons, we think, they don't have a charge and they're really not responsible for reactivity, but they have a really important job. They have something called they have something called nuclear forces. Nuclear forces are really important for holding the nucleus together. If you can imagine what would happen, you have all these positive protons together in the nucleus. They would never be attracted to each other, and they would never stay together. They would blow apart, literally, because a group of positive protons would never stay together. So these nuclear forces act as little buffers that keep them from falling apart. The electrons then are all about reactivity. They have all the power in determining how reactive or how non-reactive and what things an element will react with. And that's about it.